everybody. Would like to welcome you to today's session on high-performance computing. Just Christine introduced, my name is Jonathan Dudley, and I'll talk to you a little bit today about how the ANSYS software suite utilizes HPC. Before I get started, I'd like to let you know there'll be 4 short survey questions that will pop up throughout the talk today, about 30 seconds apiece. If you could take your time to answer those, we'd appreciate your feedback. Okay, so I'm going to start off by giving a background of the company, and then we'll get into the meat of the conversation of the agenda today, and the HPC background, and why we should be using HPC, single memory processing versus distributed memory processing, parallel processing, licensing, and a little bit of what we mean when we discuss HPC terminology if you were considering building your own machine and what you could benefit from. So CAE Associates is an engineering consulting firm who specializes in numerical methods. We've been a channel partner for ANSYS since 1985, providing sales, support, and training of just about everything related to the ANSYS software suite. And let you know that we even customize our training if you were to need it. We just need to give the company a quick call, and we would work with you to get that arranged. This presentation is one of many e-learning seminars we're going to do throughout the year, and one of many that have been posted in the last couple of years as we try to grow our e-learning seminar series. You can view the previous seminars at our website or on the YouTube channel shown below. And further, I'd like to say that if you're pursuing your PE license, you can get continuing education credit for this. If you're a New Jersey or New York resident, I need to remind you to be sure to fill out the presentation, the questionnaire, short survey after the presentation. So CAE also on their website also offers a resource library that's a very useful tool. You can look at our past consulting case studies, conference and seminar papers, some software demonstrations, and there's a handful of useful macros and scripts that are available through you to download. It's very convenient and searchable, so you can find what you want with built-in filters so you can query your searches rapidly as possible. We're also continually trying to develop our blog session as we try to get more and more mature with blogging. We offer blogs that are related to the beginning engineer in the field and also to the more advanced users in the ANSYS software suite. And again, I'd just like to mention that if you have any questions or any comments about blogs that you think would be an interesting topic that you'd like to know about, go ahead and give us a call and let us know, and we'll see if we can integrate it into our blog series. CAE's current ANSYS training schedule can also be found online at our website, on our calendar. What's interesting in 2015 is for the first time when I'll be offering online training classes will be available. And again, you can look at the calendar, and it should be clearly labeled which are online and which are being offered on site as usual. And as I said a few slides ago, we also have the capability to tailor our training to whatever your company may need. It's just a short phone call away, and work with us, and we'll see if we can arrange what's needed to be done. So with that, with a quick introduction there, I'd like to move on to actually what the meat of today is about and the background of HPC and why we should be using it and what the benefits are, along with licensing considerations. So why should we be using high-performance computing? I mean, at this stage and in this decade, actually, it's pretty obvious that most computers have parallel processing capabilities built within them. And quite honestly, if we're not utilizing HPC, we're not removing the limitations that we need to from our engineers and then the software utilization. In essence, what we're attempting to do is increase the speed that we can turn around an analysis. Or further, we can also add more physics to our capability by solving larger problems and resolve more physics of interest. We can also have more efficient parametric studies. I mean, if you imagine on a current machine now that we can do, say you can do 100 points in a 24-hour period with the use of parallel processing, you may be able to double or even triple that output and add more points for your design studies. And again, it vastly increases our ability to do design optimization, either from more points perspective or from a more accurate simulation with the same number of points. So ANSYS has been working very hard in the last 10 or 15 years in ensuring linear scalability for their software suite, and you can see in the chart I guess my chart's not advancing. I have to apologize. I was looking at the wrong screen. So we are now down to YHPC slide here. So I just caught that. I apologize for that. So I was talking about the chart on the upper right hand slide here that where ANSYS scalability has been linear over the past few years, and they now can scale linearly out to 128 cores. This is for the mechanical product. For the CFD consideration, there's a linear scalability much further out if required. And with a linear scalability, you also would expect to get a linear speed up per simulation for a fixed run. So keeping in mind, ANSYS likes to present a lot of their charts with these core solver ratings, and the question is always asked, what does that mean? And a core solver rating is nothing more than the number of jobs of a current run that you're doing you could expect to get done in a 24-hour period. So you'd collect all your CPU time usage on a particular job and divide 24 hours by that number, and it will give you a core solver rating. So again, we're looking to reduce our turnaround time. We can examine our design iterations much faster. And as I said previously, we can simulate larger, more complex models, all by the utilization of high-performance computing. So how do we access the high-performance computing in the ANSYS product suite? Is pretty much it's as simple now as just calling and activating an HPC license. We have 4 options available in terms of our HPC licensing. The first option is a single HPC license, and you can think of this as a per core or per GPU card acceleration. So you can buy a single HPC license and you can add on 1 core at a time or 1 card at a time. Or you could choose to add an HPC pack where you can buy packs in groups of 8, 32, 128 cores as shown on the upper right-hand side slide. But a point I want you to keep in mind here is that if you were to buy an 8-pack HPC license, for example, it'll give you the ability to run 8 cores on 1 single run. But if a single user submits an HPC job and requests 4 cores, it's going to check out that entire license with 4 cores sitting idle. Another user will not be able to access those cores. You're going to check out the entire license, either whether you use all the cores or not. For high-end computing, ANSYS also offers an HPC workgroup license. And again, here, this is where we're looking at getting into core counts that are maybe in the hundreds or thousands, and you can share the cores across many simulations and many runs. And again, of course, you got to balance the cost versus your license. And for the people that are interested in do a large amount of their work with parametric studies, we can also lease or you can purchase an HPC parametric pack that enables the simultaneous execution of multiple design points while utilizing just 1 mechanical license. So, for example, if we were to try to run a parametric study with the HPC pack and we had 10 design points to do, we could still only submit 1 point at a time because you only have 1 mechanical license available. But if you were to add on the HPC parametric pack with 1 mechanical license, you could utilize and run more design points at one time, depending on how that parametric pack were set up. So at this phase, we're going to pause and take our first poll. Okay, so I appreciate your feedback on that poll, and we'll move on. So let's jump right into the discussion about shared versus distributed memory. In my experience in tech support calls today, I get a lot of questions about should I be utilizing shared memory or distributed memory. And in essence, the trend is ANSYS is continuing to develop most of their solvers, and the preference is to use distributed memory whenever possible. Now, there are certain sets of runs, certain solvers, certain arrangements where shared memory configuration will still run a little better than the distributed memory, but in general, in most cases, distributed memory is preferred. So what's actually meant by shared memory is if we think of a single node or a single computer with 1 motherboard, you have one pool of RAM, and each core that's on that motherboard, each processor core is going to access the data from RAM from that shared pool, from the whole database. Where distributed memory, what's interesting about distributed memory is it can be run on either a single node machine or it can be utilized across many nodes. And then in practice here, what we're actually doing is taking our RAM and breaking it into pools that match each core. So if you have a 4-core job, as shown on the lower right-hand side, we're gonna build 4 memory blocks that associate and talk directly with each core, and it's a one-way passing. So distributed ANSYS architecture, in essence, if we think of DMP processing, and we have the ship on the lower left-hand side, what we're in essence telling the ANSYS software that we want to do is we want to take this one big problem and we want to decompose it into n blocks, where the blocks correspond to the number of processors, the number of cores that we're requesting to run the job on. So once we break the problem into these n pieces, we're going to solve each of those pieces individually on designated and dedicated cores. Once the solver completes its job, we got to send it back to the main memory bank and reassemble to update the boundaries around those blocks. So we're going to have communication required across the boundaries as necessary. And as I mentioned before, the DMP can be used on a single or on a cluster type environment, where SMP is limited to a single node only. So DMP is available on the SPARS, PCG, and LANCOS. All support the distributed memory solver. And the benefits are the entire solution phase is parallel in of itself. You get better speed ups. You can achieve up to 4 times speed up on 8 cores, which is very difficult, if not impossible, to do with shared memory. And it can be used for large jobs where you're running hundreds of cores, and it also distributes the utilization of resources across many nodes. And the memory usage and the disk usage is also scales, and in terms of read-write speed, we can access parallel I/O, which can become very important for mechanical runs because they're intensive I/O operations. So a quick plot showing what I mean by the DMP versus SMP in terms of the turnaround. We ran a simple 6 million degrees of freedom problem that involved plasticity and contact and volt pretension. We ran it 4 load steps to getting an idea of how the shared memory versus distributed memory would perform. And the chart clearly indicates that under 4 cores, the benefit of one over the other is not that advantageous. But when you start to parallelize out beyond 4 cores, the distributed memory becomes much more effective than the shared memory solver, as illustrated by the red line on the chart on the lower right. So in essence, if we're going to run anything greater than 4 cores, it's probably good practice to start with a distributed memory solver. And even at low cores, you don't really slow down by utilizing the distributed memory solver for most problems. So how do we access the parallel settings inside the APDL environment is actually pretty straightforward. When you launch APDL from the launcher, there's a tab called High Performance Computing, and this is where all your options are going to lay. You have a little radio button if you wanted to use shared memory, but if you want to use distributed memory, MPP, you're going to select that radio button. And for the MPI type, again, it just depends on which libraries you want to use, but in general, what we have found is PCMPI, the default selection, works fine, but your computer may experience a slight benefit using Intel libraries, for example, if your computer's been optimized with Intel compilations. My recommendation to you here is just to try each to see if you notice a different scalability in your runs. But in general, even if you do, it should be on the order of 10%, likely not more than 20%. If you wanted to run distributed across multiple hosts, it's simply down here where you see me moving my mouse around, we can add the different hosts, the different nodes, and select them to our list, and then simply specify the number of processors that we want to run across those hosts. Now, that's not the number of processors per host, it's the total number of processors. And then if we want to use shared memory, we click the radial shared memory button, we can specify the number of processors, and the GPU acceleration that I'll talk to in a couple of slides is as simple as a click of a button with that little checkbox button. And now, going back to the distributed memory, if you wanted to enable GPU acceleration, you still can. It just doesn't happen to be on the same page. We have to go back to the Customization Preferences tab, and we have to add an additional parameter -ACC NVIDIA to enable GPU acceleration with distributed memory. So from a fluids perspective and from CFX, I'm going to start out by mentioning if you want to do GPU acceleration, it's not available in CFX. It's only supported in Fluent. If we want to enable parallel processing in CFX, it's our first box here on the right, on the left, and we'll simply go to our run mode and select which platform library that we want to choose. And again, for single node applications, platform MPI tends to run a little bit better than the Intel MPI, but this can be machine specific. So again, I'd recommend that you test the platform and distribute it on your machine to see which gives you a little better turnaround. And it's hidden here, but if this window were to go away, I can simply specify the number of processors right below that, and then we could submit our run, and it would be going in parallel. So for Fluent launchers, it's very similar. We have our processing options that I've highlighted in the red box. You select serial or parallel. Obviously, if we want to go parallel, we're going to be parallel. And we select the number of processes and or if we want to use GPU acceleration of this GPU per machine. Fluent also has the ability to have a couple more advanced parallel settings. So in that environment, we can select the parallel settings tab, and we have the ability to specify our interconnects and our MPI type, just like we did in APDL a second ago, and the ability to select whether we want to run shared or distributed memory on a cluster. The interconnects become very important if you're running across multiple nodes and you have InfiniBand, QDR, FDR. You want to make sure you're telling Fluent how to communicate properly to take advantage of all your speed. So there's two common types of HPC, and actually a third that I'll mention briefly. The HPC, let's start with just a workstation. A workstation that's at our desk nowadays, as I mentioned at the beginning, is now a parallel computer. It's pretty hard to find a computer that doesn't have at least 2 cores available on it. So a workstation HPC is just the computer sitting at your desk, and if you think of an HPC cluster, it's in essence maybe 10, 20, or even just 2 of these connected together through some kind of external connection that's either InfiniBand, gigabit, or some kind of fiber, so each computer can talk to each other. For an example of where we're at today in terms of HPC clusters, the Department of Energy has the largest supercomputer, I believe, in the world at this phase, where it's a one computing system with 1.6 million cores available to its users. On a single desktop computer, I believe Intel Xenon chip has just released an 18-core chip. So for a quad socket motherboard, we're getting up to 72 cores on sitting at your desktop now, which is why I make the comment that every computer that we use has parallel capability nowadays. And the third option that's not shown here is just a variant of the HPC cluster. There are now companies that are offering companies and users the ability to lease time on HPC clusters that we call cloud computing. So the cloud computing is just some build of an HPC cluster, but it allows us to go out and negotiate with a third-party vendor how much time, how many cores we need, and we can lease appropriately. Okay, we'll have poll 2 next. Okay, so I think we're done with poll 2, so we'll move on to the presentation. Okay, so at this phase, now I'm going to start talking about what makes HPC and then really the internal guts of a computer and what ANSYS really benefits from if you're thinking of where to invest your money. So in essence, the ANSYS suite doesn't really care about your DVD burners, memory card readers, wireless adapters, and power supplies. But it is going to make a difference when you're building a system, whether it's your desktop or a cluster, what kind of hard drive you select, video card selection, and of course your processor and RAM will all make a difference on how well HPC or how well ANSYS HPC performs. So as I mentioned a minute ago, nowadays the quad socket motherboards are becoming popular. Most motherboards have at least 2 sockets, so we can take 2 processors, put them on a motherboard, 2 to 4 processors, put them on a motherboard. Then each processor is further divided into a number of cores per processor, which is anywhere from 4 to 18 for the Intel family. Xenon family is a common choice. And the frequencies, how fast they're performing their operations, are anywhere from about 2 gigahertz to about 3.5. So the reason I bring this up is one of the common questions. Another question I get on tech support quite a bit is if you have 2 8-core processors on a motherboard at a frequency of 3 gigahertz running an ANSYS job, and let's say it takes 10 minutes, just to throw it out there. It takes 10 minutes to get your job done. And the particular user upgrades their computer to one 16-core processor, and they run the same job, and they find out it takes 12 minutes to run. And a lot of times the frequency is even a little faster. So let's say it's a 3.2 gigahertz processor, 16 cores on one chip, and you find out it takes a little longer to run. At the end of the day, it's not just about the frequency of the CPU. It's also about how much information you can pass through the bandwidth of each chip, how fast it communicates to the RAM. So there becomes a point where that single pipe through your single CPU is a communication between the RAM and the chip becomes saturated. And in general, what I have found through experience is no hard rule of thumb for this, but in general, what I've found is somewhere around 8 cores is the optimal setting for your bandwidth per chip. So if you want you want dual or quad core 8-core chips. Now, if Intel and company increases their bandwidth, of course that'll change as technology improves. And also our RAM scales just like the CPU, and I just put a little quick picture on the bottom to show that I think a couple years ago DDR3 RAM was the most common RAM, and it was around 0.8 to 2 megathreads per second. I think the latest released motherboards now are what we call DDR4, which is, you can see a factor of almost 5 speed up in the RAM. All of this will make a big difference on how well your ANSYS simulation performs in a parallel environment. Further acceleration can be achieved by using graphical and co-processing units. I'm not going to distinguish between co-processing and GPU acceleration because ANSYS treats them the same in their licensing and how it's utilized. But in general, I'm going to say that the co-processing is only supported by ANSYS Mechanical, and the only cards that are supported are the Xenon FEA 3000, 5000, and 7000 series. And the supported cards for the graphical user, GPU acceleration, is only supported by Mechanical and Fluent. And in general, you're on the Tesla and Quadro series and the high-end series. In essence, you want a lot of RAM, as much RAM as you can get on your GPU card as you can afford. And also, generally speaking, the Teslas outperform the Quadros, and the Quadro K series don't perform as well as the Quadro series cards. So the next slide is just a quick slide of the parallel performance rating with GPU acceleration for a given Fluent run. The blue chart indicates no GPUs, and the red is 2 GPUs, and the green is 3. These are all run in a distributed fashion on 4 nodes with a number of processors scaled accordingly. And in general, you see that there's kind of a sweet spot between the ratio of the number of computer cores to the number of graphics cards that are used in the acceleration. As you see, the red line tends to flatline out. So you get, on the order of 2 times, maybe 50 or 60% speed up, depending on the exact arrangement. But in essence, for ANSYS Fluent, the couple limitations, since that was a Fluent slide I was showing a second ago, the couple limitations for ANSYS Fluent are the higher algebraic multi-grid models are ideal for GPU acceleration, and the coupled problems will benefit from GPU. The segregated, not so much. The biggest limitation for GPU acceleration in a CFD environment is the whole problem must fit on a single GPU card. So if you have, in essence, rule of thumb here is if you have 1 million cells, it's going to require about 4 gigabits of GPU RAM. I think our largest GPU card now is 12 gigabits that I'm aware of. I think it's about 12 gigabits, so we're limiting ourselves to a 3 to 4 million point model, which in a CFD world isn't all that large. And the other thing to keep in mind, as the chart previously showed, is the sweet spot for acceleration with Fluent tends to be about 3 to 4 CPU cores per 1 GPU card. The chart on the lower left-hand side shows ANSYS mechanical acceleration based on your selected graphics card. So for a given run, we have CPU only on the left, benchmarked against the Quadro series, the Tesla, and the Quadro K series. Again, verifying what I told you a minute ago, that the Quadro K series don't tend to perform quite as well as the Quadro series, and the Tesla cards tend to be the best. But again, each problem you can have a little bit different behavior. Sometimes the K card can perform better than the Quadro card. It just depends. So these are just generalities. And a couple rules of thumb for ANSYS mechanical: if you're going to use GPU acceleration, you want models that are on the order of 500,000 degrees of freedom or higher, and it is preferred that you run in a distributed memory parallel environment. For problems, again, that are greater than 5 million, you're going to need at least 2 cards or one very large memory card. For PCG and JCG solvers, they recommend having MSave off, and models that tend to have a lower level difference are better suited for GPU acceleration. So the GPU co-process and licensing agreements, it works just like adding a core onto your licensing. So in essence, if we look at one ANSYS HPC pack that allows a total of 8 HPC processes, we could run 6 CPU cores per job with 2 GPU cards. That's not, the thing to keep in mind here is the licensing is not enabling GPU cores, it enables the whole card. So you have 6 cores and 2 whole cards you could run, or 4 cores and 4 whole cards you could run. So that's very beneficial if you're going to use GPU acceleration. So we'll take poll 3. Okay, so I think we have completed poll 3. We'll move on. So at this phase, we've talked about acceleration possibilities through additional cores, through adding a co-processing a GPU, but not to be forgotten, especially for mechanical jobs, is your choice of hard disk. Generally speaking, there's 3 conventional choices for building your computer in terms of storage space. You can go the conventional SATA configuration, pretty standard now, 7200 or 10K RPM drives. These are ideal for mass storage, and they're the cheapest per terabyte, if you will. Another option is serial attached SCSI or SAS drives that are upwards of 15K RPM drives. These are ideal scratch space drives. I'll get back to this in a second, exactly what I mean. And your third choice is solid-state drives. These tend to have the fastest read-write operations. They require lower power. They're cooler and they're quieter. There's no mechanical parts, right? So they arguably should last longer, but they have not been tested, and they haven't been out in the field long enough and utilized by processing by a software like ANSYS that is going to constantly read and write to them to have a good database to really believe that they're going to last longer than your mechanical drives, but in theory they should. They're ideal for an OS drive, and the cost per gigabit is much, much higher than the other 2 options. In general, for a solid-state drive, the cost becomes way too prohibitive to garnish a couple terabytes worth of storage. So the direction that we go at CAE Associates is we tend to build our volumes. We tend to build our computers with a volume that's serial attached SCSI that's striped in a RAID 0 fashion. ANSYS Mechanical will see a huge benefit from this. You run much faster. As I mentioned before, it's intensive I/O. The catch-22 here is if you happen to be running on a cluster that's a distributed memory multiple node cluster, you actually could benefit even more if you ran your drives in an environment that's Lustre. It's a Lustre-mounted volume where it enables parallel I/O. But for single node applications, definitely you want to try to go serial attached SCSI. And then what we tend to do is have an additional volume that's built out of 7200 RPM drives, data drives that we use to back up our data on. When our runs are complete, we'll pull it off the SAS drive. So the interconnects for an internal single node computing system are not that important, other than to mention the fact that as everything improves technology-wise, so does the internal connection. So you look at the history of the PCI slots, so version 2, 3, 4, you can see how the speeds are continually going up. But in general, this slide is more geared towards external multi-node configurations where we're going to talk across nodes. The recommendation for mechanical APDL is that you require at least 10 gigabit interconnects when you're doing distributed memory processing across multiple nodes. We prefer InfiniBand, and for very large clusters, FDR is preferred. So in general, the testing that has been done on a Cat5 cable indicates that because of the intensive I/O, you actually get bottlenecked at the interconnect. So without the 10 gigabit, you really do not see any benefit for distributed processing in a mechanical environment. And you don't see near the speed up in a CFD environment either. So the 10 gigabit interconnect is recommended for both, actually. So the basic guidelines, kind of common sense, probably all of you realize this, faster cores equals a faster solution. And again, I'd like to have a couple stars there because it depends on your whole system environment, as I was talking about before. If you take a 16-core processor versus 2 8-core processors, that statement may not be exactly true. But in terms of the frequency speeds, that tends to be the case. Faster RAM is a faster solution, and you must be aware of the memory bandwidth, as I mentioned before. Faster hard disk, faster solution, especially for mechanical and in the intensive I/O. And we recommend a RAID 0 for multiple disks, and for your scratch space, we recommend SSD or SAS, and even better for a parallel file system when you can do it. So the general rule of thumb is you're going to want to configure your systems with 4 gigs of RAM per core. Maybe you may want a larger pool of RAM if you're doing large mechanical jobs. There's really no benefit to hyperthreading unless you're continually running very low core counts, hyperthreading and turbo boost. And at this phase, hyperthreading is actually recommended to be off, so the low core count is more in line with for turbo boost. And as a summary, faster is better, more is better, but it always becomes a trade-off and balance between your budget and the performance that you're requiring.